Well, what I want to do today is I want to talk about some results in A-level mathematics. I think, understanding where mathematics comes from is really, really important. If you've got questions, please put questions in the chat. I can try to answer them either at the end or perhaps during the talk. I may not always immediately see things that are put into the chat because I'll be looking at a different screen to write on. Okay, so I thought I'd start the talk with a quote from David Hilbert, who is a great mathematician. We must know, we will know. And this is really what we want from mathematics. We want to know things, to know why things are true. And a lot of mathematics is about things like pattern spotting, but spotting a pattern does not mean that you've actually, you know it's necessarily true. You want to prove it. And at the very end of the talk, if we have time, I've got a beautiful pattern to show you, which turns out not to be a pattern. So what I've got for you today is some examples from trigonometry, an example from logarithms, and then at the end, I'm going to talk a little bit about the rules of differentiation and have an introduction to proof by induction, coming back to the rules of differentiation with induction. So let's start off with something that you've met a long time ago. When you first meet trigonometric functions, you have a right angle triangle, and there's an angle, which I'm calling theta, side opposite, the adjacent side, and the hypotenuse. And you're told to define the trigonometric function sine and cosine in this way. Sine of theta is opposite over hypotenuse, cos of theta is adjacent over the hypotenuse. And from these definitions, lovely identities follow. So for example, sine squared theta plus cos squared theta. Well, this notation here it's sort of funny old notation, isn't it? What it means is sine of theta all squared, but we have to live with it. So sine of theta squared just means you take that, you square that. Cos of theta squared, you take that, you square that. So these are two fractions and they have the same denominator, the hypotenuse squared, so we can put them on a common denominator. And then when you see that and you look back at the triangle, which ancient Greek are you thinking about immediately? Anybody want to shout or put it into the chat? This squared plus this squared?
Pythagoras.
Is 1. So the ancient Greek, exactly, Pythagoras. Somebody sent me a message. That's Pythagoras' theorem. O squared plus a squared is equal to h squared from Pythagoras' theorem. So therefore, the h squareds cancel and it reduces to 1. And we have this lovely result that sine squared plus cos squared is 1. So now we've warmed up a little. Let's look at the next proof. So I want to look now at a slightly more sophisticated identity. I'm going to look at two identities in trigonometry. And I want to look at the sine of a plus b and show that it's sine a cos b plus cos a sine b. So to do this, I mean, there are lots of different proofs of this, but the one I'm going to share with you today or discuss with you today is we take a triangle and we have an angle, a plus b, and if we draw the perpendicular through the angle down to here, then the two parts of this angle that it's dividing a plus b into, one of them I'm going to call a, one of them I'm going to call b. Now, one of the things about proving things that I think we just have to get our head around is that we need to give things names. So you might want to prove this identity, which only involves angles A and B, but to get there, follow that journey, we have to have names for other things in our triangle. So what I'm going to do is I'm going to call this side of the triangle P and this side of the triangle Q. And I'm going to call the height of the triangle this way little h. And then I've taken this triangle and I've just copied it and pasted it here. But now I'm going to drop a perpendicular here and call this height capital H. But this side, which is the base of the triangle, viewed in this way, if that's the height, is still Q. And the proof that I'm going to use is based on the following idea. The area of this triangle is the sum of this area and this area. So these two right angle triangles, you add their area together, you get this total area. So let's work out the area of the triangle. And the area of the triangle is, of course, half the base times the height. So area is a half base times height. So that's a half. The base is Q. We can see that here. The height is capital H. And now I just want to rewrite this slightly. And what I want to do is I want to rewrite this involving the sign of a plus b. Because what is the sign of a plus b? A plus b in terms of h and p? Anyone type something in the chat or shout something? Sign of a plus b? Thank you. Somebody sent me a message. It's h, the opposite, over. So I'll just get rid of that. So it's h, the opposite, over p, the hypotenuse. So if h over p is a plus b, sine of a plus b, p times sine of a plus b is h. So I've got a half q p sine of a plus b. So this is our expression that we're going to use for the area of the whole triangle, and it involves the sine of a plus b that we want, and it's also very symmetric, which I like a lot. It involves p, which is the length on this side of the angle, multiplied by q, the length on this side of the angle. And symmetry is something that's often very helpful to us. So now what we want to do is to say, well, our area, our total area, is A1 plus A2, where let's say that this is A1 and that this is A2, the areas of these two right angle triangles. And so again, what I'm going to do is I'm going to say the area of A1 is, this is the height, this is the base. So again, I've got to give it a name. And again, as I've said before, this is something we need to do a lot in proof. We just have to give something a name. So I'm going to call this one, let's say I'll call this one X and I'll call this one Y. So that's just X is this length, Y is this length. So A1 is a half the base, which is X, times the height, which is H. So we're going to get a half XH. And in the same way for A2, it's a half, and then it's Y times H. And the half factors here are nice, they're common. So when we equate this to all of this, the halves will cancel. But can we write X in terms of the angle B? Well, yes, we can. X divided by Q is the sine of B. So X is Q times the sine of B. So going back to here, we have that our area is a half, and X is Q sine B times H plus a half. And in the same way, we look at this triangle now. Y over P is the sine of A. So P times the sine of A is equal to Y, and that's going to be multiplied by H. So now we want to equate this to this. Sorry, go back. We want to equate this to this. And you can see here we've got a Q, but it would be very nice to have a P here as well for the other length, because then the QP factor would be common and would cancel. And we can do that. But what it is that we have to do is, although we've got H here from looking at this triangle, to replace H in terms of P, we look at this triangle, which also has P. So which trigonometric function of A involves H and P, please? Exactly. Thank you very much. The cosine. The cosine of A is H over P. So H is P times the cosine of A. So what we get here is a half, and we're going to get a P. So I'll just write that now in alphabetical order. PQ, sine of B, cosine of A, plus, and then we do exactly the same thing here, but we want, in this case, to write H in terms of Q. So we use this triangle and we get the cosine again. The cosine of B is H over Q. So H is Q cosine of B times sine of A. And now we're making our statement that these two areas are equal to the total area. So this is equal to a half QP sine of A plus B. And I hope we're all extremely happy, because if we look at this equation, the halves will cancel, the PQ factors will cancel, and we are left with, from this side, sine of A plus B is equal to, and then I'm going to just choose to write this term first because it's the way I remember it. I have the term with sine of A first times the cosine of B. And then from this term, I'll write the cosine of A times the sine of B. So with that, we've proven this identity. And I think proofs are hard. You know, what we've had to do here is we've had to introduce new names for things. But what I would really encourage you to do afterwards is to try to do this again on a blank sheet of paper. You know, a friend of mine is very into poetry. If he really likes a poem, he tries to learn it off by heart. And I think, you know, in the same way with mathematics, learning a proof and being able to reproduce it on a blank sheet of paper is really good. So let me now just make a comment on the next slide, because I've had a message which is a very, very good message. This proof here is, of course, inside a triangle. So all of the angles, the sum of the angles have got to be less than 180 degrees, or pi if you're using calculus. So does this just work for triangles, this proof? Well, actually, there is a generalization of how to define sines and cosines, which I just want to mention, but I think that would be a completely different talk to discuss how it works. So what we do is we draw a unit circle. So that's a circle of radius 1 centered at the origin. And then we say, well, the radius of the circle is 1. So if I just draw a line and drop a perpendicular down to the x-axis, and I say this is my angle theta, so I'm measuring it anti-clockwise, then this distance over this distance is going to be the sine of the angle theta. That just follows from the definition in terms of right angle triangles. And because the radius here is 1, this height is the sine of theta. So the y coordinate of that point is the sine of theta. And in the same way, the x coordinate of this point is the cosine of theta. Cosine of theta over 1 is the cosine of theta. And to generalize, what you do is you say, okay, if I take this as my definition, that the coordinates of the point on the unit circle, the x coordinate is cosine of theta, the y coordinate is the sine of theta, and then for any angle, I just rotate around the triangle, maybe more than once. And if I want a negative angle, I rotate backwards. In that way, I can define cosine and sine theta. And there is a proof, which I've not got time to go through today, but I could send you a video to a proof if anybody was interested, showing that the rule for sine of a plus b is still works. And this approach to thinking about trigonometric functions is something that if you've not seen it before, you will see generalized more at university. So all of these things do generalize, but I still think this is a rather beautiful proof. Okay, so I want to give one more proof about logarithms, and then we're going to come on to the main meat of today's talk. So what are logarithms? Well, the basic idea is that they are the inverse to power functions. So if you say that y, whatever it is, we just give something a name, is b to the power of x, then we say the logarithm to the base b of y, and I'm putting the modulus sign here because I want everything to be positive, but if b is positive, b to any power is positive, but I still feel happier putting modulus signs. Log to the base b of y will be x. So what it is it's the log to the base b of b to the x. And if you can write the argument of the logarithm as the base to a power, then the logarithm is that base, is that power. So logarithm to the base 10 of 100 is log to the base 10 of 10 squared, because that's what 100 is. So what's the value of the log, please? Could people perhaps type it into the chat? Exactly, perfect. And then it's 2, and then just one more while we're at it. What is, let's say, logarithm to the base 2 of 8? Exactly, I'm getting 3s. Logarithm to the base 2 of a half. Yep, -1. So this is 3, and this is -1, because that's what a half is. It's 2 to the -1. So in this way, we can, once we have this understanding, we can prove the rules for logarithms. So let's just do that. I'm just taking one of them. That if you've got log of a plus b, or log of a plus log of b, it's log of the product. Now, again, we have to give things names. So let's assume that we're looking at log to the base e. The rule works for any base as long as you have the same base everywhere. Let's say we're using that special spectacular number e. Then let's look at the log to the base e of a. So let's say that a, let's just assume that a is positive, and let's say it's e to some name, and I think a natural name to give it is little a. And that tells us that log to the base e of a is going to be what? Could people perhaps type it in? People are typing in little a. Perfect, very happy. In exactly the same way, if I choose to call b, capital B is e to the little b, log to the base e of capital B is going to be lowercase b, little b. Now, I've said the logarithm is the inverse function to the power function, so we should expect to be using power functions here. And all we do is we say, well, a times b is e to the a times e to the b, and that is e to the what power? Yep, exactly. I'm getting people typing in a plus b using the rules for powers. So log to the base e of ab would be little a plus little b. And we're done. We're finished completely because we know what little a is. It's this logarithm. We know what little b is. It's that logarithm. So therefore, log to the base e of ab is log to the base e of a plus log to the base e of b. And in exactly the same way, you can prove that log to whatever base you choose of a divided by b would be the log of a minus the log of b. And you can also prove that log of a to some power, let's call it n, is n times the log of a. So in that way, all of the rules for logs follow. There are other ways of proving logs. You can see later on definitions of logarithms in terms of a definite integral for the natural logarithm. But this will certainly do us for the moment. And I personally think I feel so much happier about using something if I understand where it comes from. Okay, does that make sense to people so far? Okay, cool. So what I want to do now is I want to talk a bit about differentiation. And the idea of the derivative of a function is that it's the slope of the tangent line to the curve y is f of x at the point x. So that's what we want to have. We want the slope of the tangent line. And we can't just write it down. It's a tricky thing. This is the entire base of calculus, this question, really. So what we do is we say, well, supposing I had a different point here, say, and I could draw a chord connecting those 2 points. And here, let's say it's x plus h. I could also have h being negative, and I could be having a point down here, but let's not worry about that for the moment. It doesn't make things harder. So let's say we have here, and then here, the y coordinate of this point is the function evaluated at x plus h. And now we have the slope of the chord as this difference of the y values divided by the difference of the x values. And what we do is we say, well, of course, the slope of this line is not the same as the slope of the tangent line, but if we make this smaller, if we come in to here, and then to here, and then to here, our hope is that our function is such that this has a well-defined limit. And the key word, the really important word that we're using here is limit. This underlies all of calculus. So on the next slide, I've got a diagram I prepared earlier. And so I'm going to go to the next diagram and the next slide show you the diagram, and we're going to obtain the derivative. So I hope this curve looks pretty much like the one we had before. There are no big surprises. Here's our function. Here's our point at x, and the y value is f of x. And here's another point at x plus h, and the y value is the function evaluated at x plus h. And the slope of this line is this difference, f of x plus h minus f of x, divided by this difference, and that's x plus h minus x, so it's h. So the slope of this chord is that. And if you remember the idea that we make h smaller and smaller, we bring this point in along the curve, then what we say is we're interested in the limit as h goes to 0 of f of x plus h minus f of x, all divided by h. So we're interested in the limit as h goes to 0. And we have to invent some notation for this limit. And the notation we have is notation that you'll all know very well. It is the derivative of the function. That is our definition. Now, you may be thinking, well, why don't we just put h is equal to naught? And the answer for that is, if you put h as naught, well, first of all, you're dividing by 0, which should make you feel unhappy. And also in the numerator, you'd have f of x then, minus f of x, so you'd have naught. So if you just put h as naught, you've got 0 over 0. And I've no idea what 0 over 0 means. So this word limit is really, really important. And all of the things that you may have seen, such as derivatives of x to the n, derivatives of sines, derivatives of logarithms, they are all obtained by thinking about limits. Okay, so this is what we're going to be using, and this is what I'm going to look at in an example on the next slide. So here we go. The simplest example, well, perhaps Constant's an even simpler example, but let's not look at that. Let's try and show that the derivative of x with respect to x is 1. So we know what the curve looks like. It's a straight line with y as x, goes through the origin, and it has slope 1. If you change x by 1, you change y by 1. And now, when you are using the definition to obtain the results that we use in calculations later on, I always think it's good practice to start off by recalling the definition. So you write out the entire definition, you write out both sides of an equation. The derivative of f of x is the limit as h goes to 0 of the function evaluated at x plus h minus the function evaluated at x divided by h. So the function is y is x, so f of x is x. So what is f of x plus h, please? Yep, I'm getting people sending me messages saying that it is x plus h. And I think this idea of understanding what the function means is really important. So, if you say that, x plus h is 7, f of 7 is 7. So if it's x plus h, it's x plus h. So therefore, the derivative of our function, which is just x, is the limit as h goes to 0 of x plus h minus x over h. So x plus h goes there, and then we subtract our function at x, which is just x. And we see the lovely thing that the x's cancel, and we are left with h over h. And h over h, of course, cancels to 1. So we obtain the limit as h goes to 0 of 1. Now, can people hear me? Okay, I had a message. Somebody said I was muted. Maybe it's their sound.
Yeah, I can hear you fine, Martin.
Okay, thank you. So if there are problems like that, there will be a recording afterwards. So I hope that will help people. Okay, so now, if you change h, do you change 1? A silly question, I hope. You don't. 1 is 1. So as h approaches 0, 1 is unchanged. So this limit is 1. So what we've seen is, from our definition of the derivative of x with respect to x is 1. And we're going to be using that later on. And as I said, all the derivatives of all functions are obtained initially in this way. So let's look at a slightly more sophisticated example. Let's say that we want to differentiate a negative power of x. So we're going to differentiate 1 over x. Now, again, the first thing, in my opinion, that you should do is you write out the definition. Here's the definition of the derivative. So the derivative of 1 over x is the limit as h goes to naught. And now because this is a fraction, I really don't want to write fractions over h. Then you get these sort of triple decker things, which look really ugly. So I'm going to write this as 1 over h times the difference of the functions. It's just much more attractive. So what is f of x plus h? Our function f of x is 1 over x. So what is f of x plus h? What do I put here, please? Good. I've seen a couple of examples where people are using brackets. So what it should be is 1 over x plus h. Again, if your argument was 7, you'd have 1 over 7. If your argument is this, it's 1 over all of this. Okay, thank you very much. So we have this difference of terms. And now we'll just take the limit as h goes to naught, 1 over h. And this difference of fractions, we do the obvious thing. We put them on a common denominator, x times x plus h. And in the numerator here, I'm going to put an x. And now if you just look at this one for a moment, we'll finish this off in a moment. The x over the x would cancel. You'd be left with 1 over x plus h. That is that term. And then here we have minus. And then if I put x plus h here, the x plus h's would cancel with that. I'd have a 1 over x left. But I've made a mistake here. What do I need to do to make this term correct? Yep. So either I make this minus h, or, which is what I'm going to do, I put brackets around it. Got to be careful with minus signs. So now, again, look at that. The x plus h would cancel with that. You'd be left with minus 1 after the cancellation over x. That would be that. So now, the x's are going to cancel. We'll be left with minus h. And then the bottom, I'm just going to expand the brackets. We have h times x plus h. And again, we have this beautiful result that h is cancelled. We're left with a 1 in the numerator. And now we're in this safe position to take the limit as h goes to naught. So this is what we're always trying to do when you use the definition. We're trying to work out some way of writing it such that we're not going to divide by 0. And because these h's have cancelled, we're not dividing by 0 as h goes to naught. So here we've got minus 1. That doesn't change as h goes to naught. This is just x, and x plus h goes to x. So what we obtain is the derivative 1 over x is minus sine 1 over x squared. And that is our result for the derivative. Now, you can extend this to higher negative powers. You can extend this to fractional powers, all such things. But what I want to do now is I want to talk a little bit about the product rule of differentiation. So the product rule of differentiation, I'm going to mix up the notation a little bit, so perhaps I should apologize for that, I don't know. The derivative of two functions, I'm calling them u and v, multiplied together is, and now I'm using Leibniz's notation on this side, it's the derivative of u times v plus u times the derivative of v. So what I've got here, and we're going to see this as a general structure, is I'm differentiating the product of two functions. So I have two terms. They're identical, except in the first term, I differentiate the first function, and in the second term, I differentiate the second function. So that's the product rule of differentiation. And what I want to do is I want to ask now, what happens if you've got the product of three functions, u, v, and w? And what I'm actually trying to do here is, in a way, is to sort of introduce some of the ideas that are related to proof by induction in a moment. So again, when we're proving something, what we need to do very often is we need to introduce notation. We need to give things names. Now, I don't have a product rule for 3 functions, but I've got one for 2 functions. So why don't I call v times w y? I mean, these are functions of x, their product is a function of x. So then the derivative of u times v times w is just going to be the derivative of u times y. And I'm not putting the explicit x dependence in here just to save time. And now we know how to differentiate that. We just use this, but instead of calling this v, we'll call it y. So that's nice and straightforward. It's u derivative times y plus u times the derivative of y. And now what we do is we use the derivative of u times y. Sorry, I'll get rid of that. We'll use that the derivative of y is the derivative of v times w. So it's the derivative of v times w plus v times the derivative of w. I think this way of writing the product rule is really lovely. You know, it's very systematic. You just take what you have here, you write it twice, differentiate the first one, differentiate the second one. And now we just substitute that into here, and here we'll replace y by v times w. And what we obtain, go into purple for it, is that the derivative of u times v times w is, well, our first term is the derivative of u times y, which is vw. So it's u derivative times vw plus u times, and now I'm opening brackets, and it's derivative of y, which is derivative of v times w plus v times the derivative of w. So let's expand the brackets here. And what we see is this very, very attractive result, that it's derivative of u times vw plus u times the derivative of v times w plus u times v here times the derivative of w. So if you've got a product of 3 functions, you just write the 3 functions out, sum of 3 terms, differentiate the first, differentiate the second, differentiate the third. Question: if you had a product of 4 functions, how many terms would you need to add together? Exactly, 4 terms. You would be adding 4 terms together. And you can generalize this, and you could use proof by induction to prove a general statement in that way. Okay, let's just do a quick example of this. If you were to differentiate x cubed, well, one way of understanding x cubed is just to say it's x times x times x, and you could use the product rule in the way that we just said you can set it up for products of 3 functions. So we write out x times x times x 3 times, and then we differentiate the first x, differentiate the second x, we differentiate the third x. I don't need brackets here because this is only derivatives act towards the right. So this can only act on this. Here, I need brackets. We're just differentiating the x's. So we're going to get 1 times x times x times 1 times x times x squared, times 1. So there are 3 identical terms, all of which are equal to x squared. So the derivative of x cubed, as you would expect, is 3x squared. Bring this number in front and reduce it by 1. Does that make sense to people? Okay, so thank you. So in the last 15 minutes, what I want to do is I want to talk a bit about proof by induction, and we're going to come back to differentiation at the end of it. So some of you may not have seen proof by induction before. And I'm going to do 2 examples, and I hope it will give you the idea. Induction, what we're doing is we're saying you have some special cases, and from these special cases, you logically prove general rules. So the example I want to look at, and there's a lovely story about this to do with Gauss that you can find on the internet, I'm sure. I want to look at the sum of the first n integers. So it's 1 plus 2 plus 3 plus 4, all the way up to plus n. And again, I'm going to have to give this a name. We have to name things. And I'm going to call it S for sum, capital S, with an n subscript. And I'll call it S sub n. So just out of interest, what is S2, please? People type it in. Yep, people are typing it in. It's 3. It's 1 plus 2. Okay, so now if you explore this, you play with it, and I think play is a wonderful verb. It's what we should all be doing with mathematics. You look at something and just play with it. If you play with it, you may spot a pattern. So you can work out S1, S2, S3. And what you might find eventually is that this sum, Sn, is given by n times n plus 1 divided by 2. You might be a little bit worried that this is perhaps going to be fractional, whereas this must be an integer because you're just adding integers. But if n is even, n over 2 is an integer. And if n is odd, n plus 1 would be even. And so that would be an integer. So how are we going to prove it? So I'm going to go through this example. And again, if you've not seen it before, I'd strongly recommend that you watch the video afterwards, try to be confident with it, and then prove it with a blank sheet of paper. So we start off with something which I think seems very sensible. We are going to just check it works for the simplest value. So S1 is 1, because we just add this, that's it, 1. We stop there. And our pattern that we've seen, our claim, is that S1 is 1 times 1 plus 1 over 2. So I'm just using this definition here. 1 times 1 plus 1 over 2. 1 plus 1 is 2. 2 over 2 cancels. So we're left with 1. And that's exactly what we'd expect. So our pattern works for the very simplest value. So we're happy, but we haven't proven it yet. This isn't a proof. It's just, this is pattern spotting, and it's checking that our pattern works for the simplest value. So what I want to do now is do something much stranger. So the second step in a proof by induction has got 2 steps. The second proof starts really strangely. So what we do is we say, well, we've got this formula, and let's just assume that there is some value of n, let's call it k, for which this is true, for which our claim is true. So, and this isn't completely crazy, because we've just seen it works for n is 1. So let's say it works for n is k. So in other words, what we're saying is we're going to assume, adding up all the numbers, 1 plus 2 plus 3, all the way up to k, is k times k plus 1 over 2. We're going to make that assumption. And then what we want to do is to say, well, if we have that assumption, can we prove the next value would work? So S of, and then replace n not by k, but by k plus 1. So we'd had S of n was n, so we'd have k plus 1 times n plus 1, so that would be k plus 1 plus 1, k plus 2, divided by 2. Can we prove this? And in a proof by induction, we always have to use our assumption. So let's try now to do this, and this is, I hope, a nice example. So what we need is we need S of k plus 1, and remember what that means. It's 1 plus 2 plus 3 plus all the way up to plus k plus 1. That's what we're trying to prove has this form. But this is the sum up to k. 1 plus 2 plus 3 all the way up to k. So that we have assumed is k times k plus 1 over 2. So therefore, s of k plus 1 is going to be k times k plus 1 over 2 plus k plus 1. And now to combine that, I'm going to divide this by 2, multiply all of it by 2, I need brackets. And then I see that I've got here a common factor of k plus 1 when I put them on a common denominator of 2. So I'll pull out k plus 1 as my common factor. And then from this term, we've got a k. And then we're adding this term, and here we've got a plus 2. And that, excuse me, that is exactly what we wanted to prove. So the logical idea is we know that this is true for k is 1 or n is 1. And we've just said if it works for this, we've just proven that it must then work for the next one. So the fact we've shown that it works for n is 1 means that we now know it works for n is 2. But if it works for n is 2, we now know it works for n is 3, because we've shown if it works for any value k, it must work for the next one. So what we've done is we've just proven that this is true for infinitely many values. Okay, so the finale that I wanted to give you, and I'll try to give it fairly quickly. Again, you've got the video afterwards, is the derivative of x to the n. So I think you should all have seen this. I'm going to try and prove it for positive integer natural number values of n. So step one is we want to check for n is 1. d by dx of x to the 1, but x to the 1 is x, and we know that that's 1. We've proven that already earlier in this talk, so that's fine. We now assume that the derivative of x to the k is kx to the k minus 1. We just take our thing we're trying to prove and just say, well, let's assume it's true for some value that we're going to call k. So now we need to show, let's think about what we need to show, that the derivative of x to the k plus 1 is k plus 1 times x to the k plus 1 minus 1, which is x to the k. So that's what we want to prove. And now, to do that, we just want to use our assumption. So we're going to say the derivative of x to the k plus 1 is x to the k times x, because this is x to the k plus 1. And we can use the product rule, which follows from our definition. That can also be proven. So we have the derivative of x to the k, and that's great because we've assumed that, times x plus x to the k times the derivative of x. This is 1. This, from our assumption, is k times x to the k minus 1. So if we look at this, we have k times x to the k minus 1 times x. So that's x to the k plus x to the k times 1. So both of these terms have x to the k. There's k of them, and there's plus 1 more of them. So it is overall plus, or k plus 1 all times x to the k. Check the algebra carefully, please, and make sure that you are happy with it. So what we've done is we've said, well, this works if n is 1. We've seen that. And we now know if it works for any value, it will work for the next one. So it will work for n is 2, but if it works for n is 2, it works for n is 3. etc. forever. So that is our proof by induction for all the natural numbers that the derivative of x to the n is nx to the n minus 1. Okay, so really we're finished. Proof matters. You need to know if you can rely on a result, when you can rely on a result. You develop tools with practice. I'm not claiming proof is easy at all. It's practice. And do try to prove results on a blank sheet of paper, and do enjoy playing with things. Does the same proof work for numbers before that number? Yes, it does indeed. If I was to say, go back to here, and if I was to put in, let's say, 7 here, then there would be 7n, 7, that would be 7. It would just sit there. You make your assumption, you put the 7 in here, 7, 7, it would all follow. A good way to practice more abstract proofs, in my opinion, it is to practice specific, concrete proofs. I mean, they can be abstract, but prove them. See how things follow from definitions. So, and a lot of this is to do with algebra and just inventing names for things. So anything that you meet at school or at college that you don't have a proof for, just try to see if you can understand the proof or at least get an idea. It's practice. It really is.
We've had another question on that final proof, Martin. Is this one only working for integer values of n?
It is. This is a proof for integer values of n. So if you want, what you can do, so I was trying to use proof by induction. Proof by induction, you typically have a label, such as this value of n here. If you want to prove it in general, then what you've got to do is you go back to our friend the definition, and you want to differentiate. Sorry, let's call it n. You want to do that for n being a positive integer. You want to see it for negative integers, and you also want to see it for fractional numbers, positive and negative. And those things can all be done. We saw an example of a negative integer, but if you wanted to prove from the definition that the derivative of x to the 2/3 is 2/3 x to the minus the third, you can do it, and it's actually a really pretty thing. The 2 and the 3 come from quite different places in the algebra that you need. Are there any more questions?
Yeah, we've had one more generally about mathematics. So we've got a student who's studying mathematics at sixth form and interested in studying it at university, and they just wondered how much different it is at university than sixth form.
So I think part of the ethos is that there is much more of an emphasis on proving where things come from. So if you're somebody who gets a little bit annoyed when you have a result but you don't know why it's true or whatever, then that maths, I think, is definitely for you. The other thing, of course, is that you are going in your mathematics modules. You will be using things, not in every module, but you will be learning computer programming. You will be solving problems with computers, and mathematics has got lots of beautiful and weird results, but it's also incredibly useful. So, I mean, we've seen this with the COVID pandemic. You can see differential equation modeling using calculus of the spread of diseases and many other things. You can look at the data that's used in data science and in statistics to better understand things. And so that's very much used in real life at the moment. Okay, somebody has asked what the pattern was that isn't a pattern. If you haven't taken further maths beforehand, would you recommend specific things to do in preparation for maths at university? The first thing, which you may think I'm talking down at you, but I'm really not. Improve your algebra. So when you're hearing something complicated, you're not worrying about the algebra. You're trying to get the big picture. Algebra skills are really important. So you know, and just solve problems and explore. And people ask for a pattern. Does further maths help? It might help with some people, but you know, on the other hand, the UK education system is quite narrow. So I think if people want to just do maths and then go on to a maths degree, certainly here at Plymouth, that's fine. I think we've got something like about 40% of our students have further maths. I hope that helps. Here's a pattern. So this is a lovely little integral. It's an improper integral along the whole of the real line, sine of x over x, and the answer for it is pi over 2. It's something I actually prove in a module I teach. And then you think, okay, well, can I extend this? So you take that and you multiply it by sine of x divided by 3 divided by x divided by 3. I apologize for writing something like that, but you see the structure. And you still get pi over 2. And you go, wow, that's wild. So then you say, well, let's put in another factor. We're going to multiply by sine of x over 5 over x over 5. And you still get pi over 2. And at this stage, you're starting to think, oh, hang on, this is really going somewhere. And you keep doing it, more and more factors, all the way up to sine of x over 13 divided by x over 13. And every time, all of these different integrals, you get pi over 2 for it. However, and at this stage you're convinced, you're thinking this is something I'm going to be able to prove. However, at the next step, sine of x over 15 divided by x over 15, it's not pi over 2, and it never is again for any more factors. So despite the fact that we've got lots and lots of examples in this pattern working, it does break down. And really this comes back to what I said here. Can you rely on a result, and when can you rely on a result? If you try to prove this here, it turns out that built into any proof, you have to assume that the numbers here, a third plus a fifth plus a seventh, that they add up to being less than 1. And when you add up to 13 plus a 13th, it's just under 1, plus a 15th, you go over 1. So the conditions that are built into any attempt to prove this are no longer valid. But I think it's, you know, I think anybody, the first time they see this, after you've seen all of these examples, you know, there's lots of other integrals written down here, you'd be convinced it was pi over 2, wouldn't you? No, good question. It's no longer the constant, it changes. I mean, it's really surprising that it's constant for the numbers adding up to 1.
We've had a question about engineering and mathematics, Martin. So studying mathematics at sixth form, what would that maths then look like if you were then studying engineering at university? Would there be a big difference, or would it be similar?
So I'm actually, this semester, I'm actually teaching engineers. I'm teaching applied mathematics to them, mechanics. So the sorts of topics that and they've had a mathematics module in the first semester. So in that, it will have involved trigonometry, it will have involved logarithms, it will have involved calculus, and it will also have used vectors and matrices. So if you're thinking about things like a force, I mean, let me just show you a force. Here's a pen, I let go, it drops downwards. So the force has a magnitude and a direction, it's a vector. So applied maths, we're looking at problems in higher dimensions. You've got to use vectors. So the sort of typical maths that people will be using in engineering is calculus and vectors. You know, if you're trying to build a structure, you are going to need vectors. Does that help a little bit to the person who asked the question?
I'll just wait and see if they type anything else in. I've got another question. I think I might bumble over this word, but bear with me. What should I do at uni and further if I want to do actuarial sciences?
Actuarial sciences.
Sorry.
So, I know a lot of people who studied with us who've graduated and gone on to becoming actuaries. So you can take straight mathematics degree and take stats modules. You could take maths with finance type degrees, and there are dedicated degrees. I mean, it really is a question of how much you like maths. If you like maths, I would suggest you take a mathematics type degree, a degree with the M word in the title. And if you want to go into finance, you should definitely take statistics modules, because, you know, statistics is very, very much used in the financial world. And again, you know, it's very different to what you've seen at school. You'll be, you know, all of this will be done on computers. You'll be writing programs to analyze data. What's the balance of pure and applied maths generally at university? You can, it depends. Typically what happens is you have a core at the beginning, which is going to vary slightly from university to university. And then at the end of the degree, after you've got your basis, you can follow the pattern that you want to go in. So you can choose to do what you want. I've also been asked about physics. So I am a theoretical physicist. Theoretical physics is extremely mathematical and uses an awful lot of what is nowadays often called pure mathematics. So, you know, you can find degrees that will be, you know, mathematics with physics, physics with maths. I mean, we've got the possibility in our maths with theoretical physics degree to study things like quantum mechanics, to do projects in general relativity, things like that. Is A-level maths more similar to UK university maths than IB maths? I don't think that's a big issue. I think the IB is a very good preparation for going on to university. So I would not worry about your qualification, whether it was IB or A level. Just enjoy it and explore it and try and prove things. I hope that helps.
Cool. I don't have any more questions that have come in. I don't know if you've got any lurking in there, Martin.
Just going back up the chat a little bit. I don't think I'm seeing any others there at the moment. So, you know, we'll send you, or Shauna will kindly send you a link to the video, and yeah. I'll send a couple of links to a few additional proofs and so on.
Perfect. Thank you, Martin. Thank you to everybody for joining us. If you do think of any questions after the session ends or after you rewatch the recording, do just drop myself an email.
Oh, sorry, I've had one more question about jobs that people get to go to do maths. One of the big differences between maths and doing, say, engineering is a vocational degree. You study engineering to become an engineer, although quite a few engineers end up going on to do other things as well. With a mathematics degree, you can do so many different things. I mean, there's really quirky things. One of our graduates is a composer of electronic music who's had his music played in places across the world, but that's very unusual. But there are lots of people work in finance. I would say probably about 40% of maths graduates end up working in the financial world. It could be actuaries looking at risk. It could be accountancy. It could be investment bankers. But there is so much else. I mean, if you're looking at, let's say, wave energy, one of our students or not wave energy, wind turbines. One of our students last year did a project on modeling the distribution of wind turbines in an offshore farm of wind turbines, how you do it to optimize with given wind configurations, the amount of energy you can extract from it. And that sort of thing that you might not think is part of a maths degree is very, very typical. We've got people who work at GCHQ. I don't know if you know GCHQ. It's the government communications headquarters, so they're spies. I'm not trying to encourage you to become spies, but what I'm trying to show you is just how weird it is. So every time you buy anything online, the encryption was developed by mathematicians, and we actually get our first year maths students to prove it and implement the method of encryption that's used by Amazon, for example, using Python. So, there are lots of things. Another destination for a lot of graduates, if they find out they like statistics at university level, is a lot of people work for the pharmaceutical companies and the testing companies on new drugs. All of these things, are they safe? You hear about, there's a new vaccine and they reckon it's 90% safe. This is all done involving statisticians. And, I knew one of our graduates was very successful when I actually heard him in my kitchen at home being interviewed on Radio 4 on the Today program, talking about the project he was on, which was to do with diabetes. So, there are very many things that people can do with maths. I've also been asked by the male-female ratio at university for maths. I would say of the hard sciences, so that's things like physics, engineering, maths stands out as having a much better ratio of female students. So I would say it's something of the order of 30-odd% of our students are female. Somebody has also said they're interested in maths and music. Would it be a problem if they did a joint honours? I would have very much hoped not. I mean, I think if you've got a mathematics degree, and basically that's going to be a maths degree, you are, and you have an interest. I mean, a lot of employers, if they're not silly, they actually are interested in the fact that you are a person, that you have got things that you're really interested in. So, I think that's, if you say, well, I did maths and music and I'm really keen on music and I play it or whatever, I think you'll find a lot of employers will respect that. I've also been asked about not being brilliant with computers. I think you should assume that you're going to be taught from scratch in the first year, and I think fine. If you can think mathematically, you're thinking logically, and basically computers are mathematical systems. And so I really would not worry about that. Just don't be put off. When you meet something at university level, expect, hey, this is going to be a bit different, and just play, enjoy. And I've had one more question. Sine of x over x is undefined at naught. Very good question. If I can just answer that one quickly. So we have this integral, sine of x over x, and the question is, what happens as x goes to 0? Well, you can show that the limit as h goes to naught, sine, well, I'll call it x, sorry. I was thinking about the derivative, sine of x over x is 1. You can actually show that that limit is 1. And there's a very nice sort of geometric proof of it, and I can send you a link to it. It's really important because if you're differentiating sine and cosine from first principles, you actually need this limit. So it's interesting and important for more than just that. Does that help a little bit with the question? Thank you.
I've just had one more pop in, Martin. I'm not sure that we offer this course or one similar, but I don't suppose you know anything about design engineering and what somebody could expect from that course.
So the only thing I know about that is that there is a master's here in advanced engineering design, and that is particularly aimed at mechanical engineers. So I think students who are interested in design and engineering are probably at undergraduate level more interested in mechanical engineering. That would be the one to look at. That would be my feeling. And again, if you're interested in any course or going to any university, just contact the university and talk to them about it. I used to be the admissions tutor for mathematical sciences here at Plymouth, and I'm very happy to talk to anybody about maths. And and I would have thought that anybody at any university is happy to talk to you. And if they don't respond to you and they're not interested, well, hey, you probably don't want to study there anyway, do you?
Perfect. Thanks, Martin. I don't have any other questions, so we can wrap it up there if you're happy.
Sorry for overrunning, but thank you very much to everyone. And as I say, do please have a go at trying to prove things on blank sheets of paper. It's a really good thing. And have a lovely weekend. Stay safe.